Need a VCA for your DIY modular? Here's a simple one I designed that uses just a couple transistors and op amps. So first things first, what does a VCA do exactly? Well, the simplest way to visualize it is by looking at an ordinary volume knob, like the one on this TR606. We probably all know how these work. Turn it to the right to in, and to the left to decrease the volume. So far, so simple. But while these have their place even in a modular synth, they've usually got one major shortcoming. They're not automatable. You can only turn them by hand. In the modular world, this is a big no-no. The whole point is being able to modulate any and all parameters using LFOs, envelopes, and sequencers. So what we're looking for is basically just a volume knob that can be controlled with a voltage. That's what a VCA is, a voltage-controlled amplifier, where a low-level voltage corresponds to a quiet, while a high-level voltage gives you a loud output signal. So if we control our VCA with an envelope, for example, we can give an oscillation a volume curve that mimics those of certain instruments. A slow attack sounds like a swelling violin. A super short attack, quick decay, and long release sounds like a plucked guitar. Now, in order to be able to design such a VCA, we need to take a step back and talk about basic boring volume knobs again. How do those work? Well, at their most basic, they're really just potentiometers set up as variable voltage dividers. Because remember, in the world of electronics, sound is just a swinging voltage. And the bigger the swing, the louder the sound. Since voltage dividers do just what their name implies, they'll divide or scale down any voltage level you throw at them. So imagine we set our potentiometer to precisely 12 o'clock. This means that these two resistances are exactly equal, giving us a perfect 50% voltage divider that slashes our sound's volume in half. Turning it to the left will then gradually reduce that volume until we get complete silence. Why is that? Because we're changing the relation between these two resistances. And that relation will determine the factor by which our voltages are divided down. To understand this on a more in-depth level, let's visualize it using the water analogy. In that analogy, we think of electricity as water flowing through a system of pipes, with voltage being pressure and current being the flow amount per second. Resistors would then be narrowings in the pipes, restricting the flow. With this, our voltage divider should start to make more sense. Because now imagine we have a steady amount of pressure applied to the top here. Since our system is wide open at the bottom, we'll see water flowing in this direction. How much? That directly depends on how narrow our pipes get, as this is literally the bottleneck here. To make our lives a little easier, let's quantify things. We'll say that both these are exactly equal in diameter. 1 centimeter. Individually, they'd let the same amount of water pass through in this setup, 10 milliliters per second. But placed in series, that amount would be slashed in half, giving us a flow of just 5 milliliters per second. So it's fair to say that there is some unused potential here. The two narrowings are basically handicapping each other. I like to think of it like this. If we were to bypass the second narrowing, we'd suddenly see 10 milliliters flowing in this direction. This is simply because we got rid of the additional bottleneck. Now the question is, where does this unused potential go when there's no bypass available? The answer is simple: nowhere. It just stays here at this point as pressure. How much? Well, since the full realized potential is a flow of 10 milliliters and we see just half of that, the remaining pressure is exactly half the pressure we apply up here. Knowing this, we can derive what happens when we change the relation between these two narrowings. If we make this one wider, we'll see two things happen. First, the total amount of flow will increase. Second, the amount of pressure at this point will decrease. This is because we partly de-handicap this narrowing, which allows for more potential to be used and converted into flow. On the flip side, if we make this one tighter than the other, flow will and pressure here will increase. An important thing to keep in mind is that when we're just focusing on the pressure level at this point, the absolute quantity of flow does not matter at all. It really is only about relations and proportions. So whether we have a total flow of 5 milliliters or 5 liters, as long as this is half of what could potentially flow with just one narrowing, we get half the applied pressure here. And if it's quarter of what could potentially flow, we get 3/4 the pressure. Okay, but so far we've assumed the pressure up here to be constant. An audio signal, as we said earlier, is a swinging voltage though, meaning that it changes over time. In our analogy, this would mean that our pressure is getting more or less intense, and sometimes even going negative, essentially turning into suction. Now obviously a voltage divider works with audio signals. So it can handle big, small, negative voltages just fine, always dividing them by the same factor. But why is that? Simple. Resistors have two properties that make this possible: linearity and symmetry. Linearity in this context means that there is a linear relation between the voltage applied to a resistor and the current that will flow through it. So a doubling in voltage will always result in a doubling in current. Same thing applies for our analogy. If we double the pressure, we get double the amount of water flowing through our narrowings. Since this is true not only for multiple narrowings in series, but also for each individual one in isolation, our potential flow model still works out the same way. Let's look at this in detail. For a doubling in pressure, we'd get a total flow of 10 milliliters instead of just 5. Add a bypass though, and we'd see a whopping 20 milliliters flow through this narrowing. Since 10 milliliters in total is still half of these 20 milliliters that could potentially flow, we, again, get half the applied pressure at this point. Cool, but what about negative voltages? This is where the second property, symmetry, comes in handy. For resistors, and for our narrowings, the direction of flow does not matter. The restrictive effect will be the same in this or in that direction. So if the pressure up here goes negative, we simply add a minus sign before all our values, indicating that the direction of flow has been inverted. But since minus 5 milliliters is still half of minus 10 milliliters, everything still works out the same, and we get half the pressure at this point. Okay, so now we know why voltage dividers are a really good fit for manual volume control. But the question is, how can we modify them to give us voltage-based volume control? Well, if you've watched some of my earliest videos, you might already be thinking in a certain direction here. Because in my VCO series, I claimed that you can use NPN transistors as voltage-controlled resistors. If that were true, then something like this should work, right? We could simply replace one of the two resistors in our voltage divider with a transistor. Then by applying a voltage to the base, we should be able to control the amount of resistance between collector and emitter, giving us a voltage-controlled voltage divider in total. Unfortunately, if you build and try this, you'll be severely disappointed. And that's because what I said in that VCO video is at least misleading, if not flat out wrong. A transistor is not a voltage-controlled resistor. There is no resistance in that sense between collector and emitter. To understand this better, let's talk about what resistors and transistors have in common and what separates them. On the common side, both components allow us to restrict the amount of current flowing in a circuit. This is why superficially they seem kinda interchangeable. Consider this example. We'll set up two separate simple circuits. One is just a resistor between a voltage source and ground, and the other is a transistor, with its collector connected to an identical voltage source, its base connected to another much weaker voltage source, and its emitter connected to ground. Now, if we tune the base voltage carefully, we can get the exact same amount of current flowing through our resistor and our transistor, about 120 microamps. This might lead you to believe that for this base voltage, the path between collector and emitter acts just like a 100K resistor. If that were true, then it would need to exhibit the same two properties that resistors do: linearity and symmetry. Let's check for linearity first. Doubling the voltage applied to the resistor will give us twice the amount of current, 240 microamps. But for the transistor, something odd happens. Nothing. We'll still see the same 120 microamps flowing through this circuit. Why is that? Because the only thing determining the amount of current that can flow between collector and emitter is the amount of current flowing into the base. And the latter only depends on the voltage at the base, not the voltage at the collector. Now, while this would already disqualify the transistor, let's also check for the second property, symmetry. What happens when the collector voltage goes negative? Interestingly, our transistor would theoretically still work roughly in the same way. We'll see a current flow between emitter and collector, but it won't be the same current just inverted. Instead, it will be a ridiculously strong current that will wreck our transistor. This is simply because the huge negative voltage between base and collector pulls a much too large amount of current into the base, disqualifying this use case without further alterations to the circuit. So it's official. Transistors are not voltage-controlled resistors. Which is precisely why this idea does not work. Since the current going through a transistor is fixed, if the base voltage does not change and the collector voltage stays positive, the total current flowing will be fixed as well. So in or decreasing the voltage up here will only change the potential, not the actual flow amount. This means that the ratio between potential and actual flow is not fixed anymore. And that's why this simply does not work as a voltage divider. Here's how this pans out in detail. Let's assume we've set the base voltage so that our collector-emitter current is exactly 60 microamps. Then the total current going through transistor and resistor is also 60 microamps. Since the 100K resistor could potentially allow for 120 microamps to flow if we bypass the transistor, the ratio between potential and actual flow is exactly 1/2. So we'd measure 6 volts at this point. Now, if we double the voltage up here to 24 volts, the current flowing will stay the same, 60 microamps. But since the resistor could now potentially allow for a flow of 240 microamps, our ratio shifts from 1/2 to 1/4, meaning we get 3/4 the voltage at this point, 18 volts. As we can see, the increased voltage simply gets added to the previous value, making this setup unusable for our purposes. Okay, but if we can't use transistors as voltage-controlled resistors, then how can we use them? Well, one of their main applications is actually amplification. Transistors can take a very small voltage swing and scale it up massively. One way to do this is by setting them up in what's known as the common emitter amplifier configuration. At its most basic, this is what that could look like. As you can see, this setup seems very similar to what we had before. There is one major difference though. We're no longer applying our oscillation to the top end of this resistor. Instead, we've scaled it down to just 20 millivolts peak to peak, and then added it to the steady voltage we apply to the transistor's base, while simultaneously connecting this point to 12 volts. Now, if we monitor the voltage at this point, we'll notice something strange. Compared to the oscillation we sent into the base, there is a huge voltage swing here that looks a lot like it, just slightly distorted. What's up with that? To answer this, we'll first have to understand the way the base voltage relates to the amount of current allowed to flow between our transistor's collector and emitter. We'll simplify things by removing the resistor between voltage source and collector for now. Here's how this graph works then. On the x-axis, we track the voltage applied to the base, while the y-axis shows us the measured collector-emitter current. As you can probably tell, the resulting plot looks suspiciously exponential, and that's because it is. In the area between 0 and 600 millivolts base voltage, we only see a super slight increase in current. But then, suddenly, it starts going through the roof. And at around 775 millivolts, we'd already see a full amp of current flowing through our transistor. Or rather, we would see if the transistor weren't already toast by then. That's because most general-purpose transistors can only handle a few hundred milliamps. And so the actual usable range is somewhere between 0 and 700 millivolts base voltage. In our application, we're using just a tiny sliver of this, since the scaled-down offset signal swings between 515 and 535 millivolts. Here's what that sliver looks like when we zoom in on it. Now, since we are using a triangle oscillation as our to-be amplified signal, we are basically moving our base voltage back and forth between these 2 points at a constant speed. So effectively, we are replicating the oscillation in the amount of collector current going through our transistor. And as we can see, for a rather small change in voltage, we get a pretty significant change in current. Knowing this, it should start to make sense why this setup works as an amplifier. Because if the current going through our transistor changes, the voltage at this point will also change. That's because we are converting more or less of the resistor's potential into actual current flow. Let's break this down in detail. So we know that our 100K resistor could potentially pass 120 microamps in this setup. And on the previous sheet, we saw that our transistor's collector current is oscillating between around 50 and 100 microamps. So the ratio between actual and potential current flow is also oscillating. Quite heavily, in fact. At 50 microamps collector current, we are using around 40% of the total potential. And at 100 microamps, that number rises to about 80%. Which means that the voltage here will swing between approximately 7.2 and 2.4 volts, giving us a 4.8 volts peak-to-peak output. This is an impressive amount of gain. Because remember, the signal we sent into the transistor's base was just a measly 20 millivolts peak-to-peak. Okay, but what about the distortion that our circuit introduces? Where's that coming from? Simple. If we take another look at the relation between base voltage and collector current, we can clearly see that this plot is not linear. It's slightly bent. And that's because it is part of an exponential curve. And so as our voltage is oscillating at a constant pace, remember, we're using a triangle wave here, the current is slightly speeding up and slowing down. And since this change in current is directly translated into a voltage swing, that voltage swing will be slightly bent as well. Tough luck. So what can we do about that? There's just one solution here, really. Use a smaller portion of this curve. Why does that help? Well, the thing about exponential curves is that if you divide them into smaller and smaller chunks, these chunks begin to look more and more linear. The one we see here is already a lot straighter than the full curve, but in order to minimize distortion, we'll have to scale our oscillation down even further. So here, our signal is swinging only between 522.5 and 527.5 millivolts, netting us a tiny 5 millivolts peak-to-peak oscillation. And as we can see, the resulting plot looks almost linear. It's not perfect, mind you, but still close enough in my books. Okay, so we'll just use a voltage divider to scale our input down even further, right? Actually, there's another way to achieve the same results, but with some extra benefits. Adding a resistor between the transistor's emitter and ground. How does this work? Well, this is where it gets a bit tricky. It works by introducing negative feedback. As we know, this entire circuit operates by having a varying amount of current flowing through our transistor and to ground. Now, if there's no resistance here, we have a direct, uncomplicated relation between the base voltage we apply and our collector current. But by adding in the resistor, we are restricting the current flow between emitter and ground. And this means that there's again some unused potential here, which manifests in a voltage at this point. How much? That depends on two factors, the amount of resistance and the amount of current. Now, because the resistance is fixed, we don't have to worry about it too much. We'll only have to ask what happens when the base voltage, and thereby the collector current, changes. Simple. If they increase, then the voltage at this point will increase as well. And if they decrease, it will be mirrored here too. Let's play this out with some actual numbers. We'll assume the emitter resistor to be a 10K. So our base voltage is still swinging between 515 and 535 millivolts. But if we probe the voltage at the transistor's emitter, we'll see that it is also oscillating between 55 and 70 millivolts. Now, since for our transistor's operation, only the voltage difference between emitter and base voltage is what matters, we need to subtract the former from the latter, leaving us with an effective base voltage swing between 460 and 465 millivolts. And voila, we've reduced it to just 5 millivolts peak to peak. But at the same time, something weird happened to our amplified signal. Instead of 5, we're now only getting about 0.1 volts peak to peak here. Now, of course, we've effectively scaled down our input to just 25% of what we fed in here before. But 0.1 volt is not 25% of 5 volts. Something else must have changed. And that something is our amplifier's gain. To understand why, we just need to have another look at our base emitter voltage graph. Before we added in the 10K emitter resistor, our signal was swinging between these 2 points up here. But now, with the resistor in place, the active range is this smaller slice that's also further down the curve. And because it is further down the curve, it is also noticeably flatter. There's just way more vertical distance between these 2 points compared to what we get down here. Which is why our output signal got so much more quiet. By moving the input oscillation down the curve, we reduced the amplifier's gain. Now we'll get to the larger implications here in a second, but first I want to talk about the added benefits I mentioned earlier. Because at first sight, this seems to be a rather bad deal. We needlessly cut down our amplifier's ability to amplify, right? Yes and no. While we did lose a significant amount of gain, we also got something important in return: stability and reliability. That's because transistors have two severe flaws. First, if you take two transistors, same type, same label, same manufacturer, and compare their base voltage to collector current curves, you'll probably notice that they don't match up at all. That's because of small variations in the silicon that they're made of. And second, those unequal curves are also heavily dependent on the transistor's temperature. Heat it up by just a few degrees and your amplifier's gain shoots up noticeably. Cool it down and the output gets more quiet. Which is why all the actual examples and numbers we've talked about so far are just rough approximations. Your mileage trying this with a real transistor will vary quite a lot. That is, as long as you don't use an emitter resistor like this one. Why is that? Simple, because of the negative feedback it introduces. Let's assume we built this circuit twice, with two different transistors. One of them naturally has a lot more gain, the other a lot less. So for the same amount of base voltage, there would be very different amounts of current flowing through each respective circuit, if it weren't for the emitter resistors and the voltages they create at these points. Now, since the potential amount of current on this side is a lot higher, we'd expect to see a significantly larger voltage at this emitter resistor. In reality though, they will just be a few millivolts apart. This is because the more the voltage here increases, the smaller the difference between base and emitter becomes, reducing the transistor's gain and thereby the collector current in the process. And as we've seen before, a very small reduction in base voltage can already give you a huge reduction in collector current. So we are essentially turning the transistor's gain against itself. The more gain the transistor has, the stronger the negative feedback and the more the gain is reduced. Conversely, if the transistor's gain is rather weak to begin with, then the negative feedback and thereby the gain reduction will be weaker as well. To illustrate this, I've drawn up 4 different plots here. These two show us the base voltage to collector current curves for our 2 example transistors without negative feedback. And these two are what we'd measure with 10K emitter resistors in place. For better comparison, I used a little trick here. Instead of measuring the actual voltage between base and emitter, I measured the voltage between base and ground. This way, we can integrate the negative feedback directly into the gain curve. And as you can see, the rather significant gain disparity between the 2 transistors is pretty much eliminated by the negative feedback, which is why they'll perform in a very similar way in our example circuit. Cool, but that's not the only benefit. As I said before, a transistor's temperature also has an effect on its gain. Normally, that effect is quite strong, but the negative feedback again really mitigates it here. Because as the temperature rises, the gain attempts to increase, which in turn will raise the voltage here, and that dampens the gain in response. Okay, but one final question remains. Why did I pick a 10K resistor and not a bigger one? If the negative feedback is so beneficial, why not use a ton of it to negate all differences between transistors and eliminate any temperature dependence? Simple, because we'd be completely crushing the gain, making this setup basically unusable as an amplifier. So in the end, choosing a value for the emitter resistor is always a balancing act. How much gain are we willing to give up for reliability and stability? That being said, the emitter resistor is not the only variable we can mess with to influence our amplifier's gain. We've got 2 more options here. First, we can adjust the value of our collector resistor, because if we increase it, then we reduce the potential amount of current that could flow. Now, since this does not affect the transistor's operation, the collector current swing will stay the same, which means that essentially it's swinging across a larger portion of the full potential, netting us a bigger voltage swing at the output. There is a hard limit here though. We can't just keep increasing the collector resistor's value in hopes of unlimited additional gain, because at some point, the potential amount of current will drop below the set collector current, starving our transistor of power and distorting or even killing the oscillation at the output. Okay, and the second option? Well, this is where it actually gets interesting for us, because the second option is adjusting the constant base voltage that our signal is riding on top of. Up until now, we've been using a 20 millivolts peak-to-peak triangle oscillation with a DC bias of 525 millivolts. So on our adjusted curve, we were moving back and forth across this tiny section. Now what we could do is move this operating region way further up or down the curve to where it is somewhat steeper or flatter. Since this will have a direct effect on our collector current swing, we should also see a change in gain, despite the negative feedback. We'll just overpower it, basically. Cool, but while we could go through the trouble of adding our scaled-down input signal to our variable DC bias before applying the sum to the transistor's base, there is a simpler, more elegant solution. Instead of adding the bias at the base, we can just subtract it from the voltage below the emitter resistor. Because remember, for the transistor's operation, only the voltage difference between base and emitter matters. And by pulling this point below ground, so below 0 volts, we can expect the voltage at the emitter to drop proportionally too. This will increase the difference between base and emitter voltage, which in turn should push up our amplifier's gain. Okay, so to try this out, we'll first set up a potentiometer as a variable voltage divider. This will be our control voltage source. Then we'll invert and scale down that control voltage with an op-amp. If you don't know how this works, I've put a link to a thorough explanation in the description. Now, by turning the potentiometer, we can adjust the voltage at this point to any value between 0 and -2 volts. Going any more negative will probably increase the collector current too much and would thereby starve our transistor. That's why I've chosen this range. And since my oscillator is pushing out a 10 volts peak-to-peak signal, we'll also need to scale the input down with a 100K 100 ohms voltage divider. To try this out, I'll set up a TL074 and configure one of its op-amps as an inverting amplifier. For the input, I'll add in the 100K potentiometer. Connect it to +12 volts and ground, and our CV source is ready. Now next to the chip, I'll slot in a BC548, which is a generic NPN transistor. The collector needs to be tied to the positive rail through a 100K resistor, while the emitter links to the op-amp's output through a 10K. Finally, I'll connect this input socket to the transistor's base through a 100K 100 ohms voltage divider. To see what's going on, I'll connect my oscilloscope to the transistor's collector, because remember, this is the amplifier's output. So right now, I've set the CV to 0 volts. Let's see what happens as I increase it. Well, this is not really what we were hoping for. There are two major problems. First, the output signal's DC offset seems to be tied to the CV and is moving around wildly. And second, the gain added by increasing the CV is so minimal, it's actually impossible to see at this scale. Bummer. So what's going on here? Well, two things. First, let's talk about the output signal's DC offset. Why does it move around so much? Actually, we already kinda know the answer. So what we're doing by changing the emitter voltage is moving the operating region further up or down this curve. But by doing this, we're not only changing the amplifier's gain, we are also changing the average amount of collector current that will be flowing while the amplifier is operating. And the more current is flowing on average, the more of our 100K resistor's potential is used up on average. Meaning that the average voltage at this point is changing as well. So effectively, the amplifier's gain is directly tied to the output signal's DC offset. Now, to try and compensate for that, we could of course turn on the AC coupling on our oscilloscope. If you don't know what that is, I've put another link to an in-depth explanation in the description. But in essence, this will remove any DC offset from the input signal. Since our oscillation is now semi-fixed to the 0 volts line here, I can turn up the scaling so we can actually see what's going on. It's a bit hard to tell because of the noise, but changing the CV really does seem to have an effect on the gain. Unfortunately, the range is definitely way too small, maxing out at a measly 250 millivolts peak to peak. And also, the AC coupling is not a perfect solution for removing the DC offset, because as I'm changing the gain, you can see that the signal goes off-center for a little while. That's just how AC coupling works. Because of these two problems, this circuit just doesn't cut it. But fortunately, we can actually salvage it by adding in a few more components. The first change we'll make probably looks very confusing at first glance. We are basically copy-pasting our transistor and its collector resistor while connecting both emitters to the same original emitter resistor. Also, we're directly grounding the new transistor's base. What's this supposed to achieve? Simple. By doing this, we are turning our regular amplifier into a differential amplifier. If that doesn't mean much to you, no worries. We'll walk through the mechanics here step by step. To start out, let's imagine that we turn down our input oscillation completely, so that this transistor's base sits at 0 volts permanently. Also, we'll adjust our CV so that we've got a steady -1 volt below the emitter resistor. Now, if our two transistors are closely matched, meaning that their base voltage to collector current curves should be close to identical, we'll see an equal amount of current flow on both paths. Why is that? Well, let's imagine a state 0, before any current actually starts flowing. In that state 0, we'd measure 0 volts at both transistors' bases, while their emitters sit at -1 volt. Since the voltage difference between both bases and emitters is a whole volt each, both transistors will equally attempt to push up their respective collector currents. But as both currents increase, the voltage at this point shoots up as well, creating the now familiar negative feedback. The kicker is, though, that both emitters are always at the exact same voltage. This means that as long as both bases are sitting at 0 volts, both our transistors' collector currents will have to be identical. Okay, but what happens if we turn the input signal back up and the voltage here starts to rise? First of all, this transistor's collector current will increase. Now, in our previous single transistor setup, this would be heavily counteracted by the negative feedback. But here, something strange happens. As the voltage at the emitter resistor increases, the resulting negative feedback is affecting both transistors at the same time. It's pretty much being split up evenly. And since the base voltage here is significantly higher than the one over here, we'll see a net current increase on this side, while the other suffers a net decrease. It's as if this transistor is dialing its collector current down to make room for his buddies. And conveniently, if the transistors are matched, that process will be symmetrical. So the amount of current gained here is the amount of current lost over here. Now we know that if the collector current increases, the collector voltage decreases, and vice versa in the other direction. So if the collector resistors are also matched, the two voltage swings at these points should be the same, just inverted. Also, their DC offset should be identical, as their collector currents swing across the exact same midpoint. Finally, the overall gain potential should be significantly increased, since the negative feedback is cut in half, split evenly between the two transistors. To test all this, I'll set up another BC548 transistor over here. Connect the collector to the positive rail through another matched 100K resistor, link the two emitters and tie the base to ground, and we're done. Now, in an actual build, you'd want to set up the two transistors as close to each other as possible, possibly even glue them together to make sure they're the same temperature. But for our testing purposes, we can be a bit more lax here. I'll use two separate oscilloscope probes to monitor both collector voltages. Right now, I've set the CV to 0 volts, so all we see is a single flat line up here. But watch what happens as I increase it. Both signals are moving downwards as their volume increases. Now, if I zoom in a bit, you can see that they indeed are inverted copies of each other. Okay, but now you might say, so what? Yes, we get more gain out of our amplifier, but couldn't we just have used a smaller emitter resistor to weaken the negative feedback? And besides, how is having two signals with their DC offsets tied to the gain better than one? Valid points, but here's the twist. If we take our inverted twin signals and subtract them from each other, the result will be a signal without any DC offset. Why? Well, since both original signals have the same offset, they'll cross each other exactly at their respective midpoints. Let's say in this scenario that would be right on the 6 volts line. Now, if we subtract 6 volts from 6 volts, we get 0 volts. From here, the two lines will diverge, which means that their difference increases. Right here, that difference is at its most extreme. 7 volts versus 5 volts. Subtract those numbers and we get a 2 volts peak for our new centered oscillation. And same goes for the valley once we move half a wave cycle ahead. And the best thing about this is that it works irregardless of what the exact DC offset is, as long as it's the same for both original signals. Okay, but how do you subtract two signals from each other? Simple, with another op-amp. Because this is what op-amps do. They subtract the voltage at this terminal from the voltage at the other. And after that, they multiply the result by a fixed internal gain. Now, because an op-amp's gain is so huge, we have to take some measures to calm it down. If we really just want to subtract our two signals without changing the resulting signal's amplitude, we can set up our op-amp like this. Here's how it works. Let's first imagine that both input voltages are the same, 6 volts. Since these two resistors form a 50% voltage divider, we'll measure 3 volts at this input. Now, for the op-amp to enter a state of balance in this scenario, the voltage at this input would need to be 3 volts as well. And the only way that can really happen is if the op-amp's output sits at a steady 0 volts. Because then these two paths are exactly the same. Two 50% voltage dividers with 6 volts on this end and 0 volts on the other. Okay, but what happens if the two input voltages start to diverge? To answer that, let's assume that the voltage here now sits at 7, while the one up here has dropped to 5 volts. This means that this input now reads 3.5 volts. Now, if it wants to get the other input up to the same value, the output really can't stay at 0 volts. Instead, it will have to make up for the difference between the two input signals. And to do that, it'll push out a steady 2 volts. Because the midpoint between 5 and 2 is exactly 3.5. Cool, so let's add this to our circuit and see how we fare. Since we've got 3 more unused op-amps on our TL074, we can pick any of those to be our signal subtractor. I'm going with the one right here. To set it up, I'll connect inverting input and output, non-inverting input and ground, and both inputs with our two transistors via 100K resistors. And that's it. We should now be able to pick up a properly centered signal from the op-amp's output. Let's hook up the oscilloscope to check that out. First, let's make sure that the AC coupling is turned off. And yeah, that looks pretty good. If it doesn't for you, you could try different pairs of transistors at this stage until you find one that matches. It's not the most precise method, but it will get you into the ballpark. Now let's try to mess with the VCA's gain. As expected, the signal stays centered around 0 volts. Great. There's just one minor thing we need to fix. If I turn the gain way up, you can see that the maximum voltage swing is just about 1.5 volts peak to peak. Unfortunately, this is still pretty far from the 10 volts peak to peak that is the de facto standard in the modular synth world. To fix this, we can simply use a bit of our output op-amp's gain. Because right now, we are only using it to subtract our two signals, not to amplify the result. How do we change that? By making the output work harder to equalize the two input voltages. And in order to make it work harder, we have to throw the relations between these resistors off base. If we make these two smaller than these two, we're essentially creating two effects that will synergize. First, the voltage swing at this input will get bigger. Because where before the 50% voltage divider was effectively halving the signal's amplitude, now we're only cutting it down by a relatively tiny margin. And second, the op-amp's output will have to push and pull a lot harder through this massive resistor to match the bigger swing at this point. Now, of course, when trying out different resistor sizes here, it's crucial that these two pairs are of the exact same value. So they need to also be matched. This is the only way we can ensure that we get a 0 volts output if the two signals are at the same voltage level. In my experiments, a combination of 10K and 470K resistors worked out fine. So let's do this final adjustment and then finally take a listen. So I'll simply exchange these 100Ks for 10Ks and these other 100Ks for 470Ks. And as expected, we can now vary the output from 0 to round about 10 volts peak to peak. Perfect. Let's hear how this sounds. Of course, when I control this by turning a potentiometer, it's really not more than an overcomplicated volume knob. So let's swap out the potentiometer for a jack socket. Now I can connect our VCA to anything that sends out a voltage, like an envelope generator. As you can hear, the volume is now directly controlled by the envelope's curve. If I play around with the attack, sustain, decay, and release controls, I can shape the sound to my liking. Cool. Let's see how it sounds when the VCO is playing a proper sequence. Of course, you can also use the VCA to shape white noise into short percussive hits. Overall, I'm quite happy with how this circuit sounds, especially considering the low number of components. Still, there's room for improvement. For example, everything lives or dies with how well the two transistors and some of the resistors are matched. Ideally, there should be some additional measures that compensate for small divergences here. So in a future video, we'll talk about refinements and additions to this design. In the meantime, be sure to check out my Patreon. You can not only support the channel there, you'll also get access to a bunch of bonus content, like a live stream replay archive or a private community Discord server. Anyways, thanks for watching and until next time. See ya!